first thing that I wanted to do was kind of get a background on how you got into the free energy movement, and then progress from there on where you see the space power generators moving and what direction you see the movement going. So maybe we could start with way back around 1958 or so is when you first started getting into this.
Well, 58 is when I graduated from M.I.T. I did government R&D work until about 1961, and then I worked for Polaroid Corporation because I wanted to get away from the military and eventually atomic bombs, which anybody who was very intelligent in the R&D business got involved with sooner or later. I have been a longtime friend and associate of Harold Edgerton, the founder of the EG&G Corporation. I met him when I was an undergraduate at MIT, and when I went to work for Polaroid in 1963, he asked me to help him teach his courses in high-speed photography, stroboscopic. And this time in the 60s, we had the Vietnam War going, and there was a rising ferment and unrest at the campus at MIT. Also, MIT was at the head of a great educational apparatus which selected the best people from all over the world to come and study science there. And in general, in the 60s, the most intelligent people in the world, the young people, were thinking about what was wrong with the system and why they had to go to Vietnam and fight in the trenches, and why the country's at war, and why were they putting together MERV guidance systems as part of a MIT course in astronautics. They couldn't quite understand things like that. And so in the midst of all this ferment, it became clear to me that energy was the basic cause of a lot of the unrest in the world and the inability of people to actualize their lives and move around, transportation. And I thought if we had something better in that department, the world peace situation would be helped, because I didn't see there was any political solution to what was going on. It was just chaotic. And for those of us that lived through the 60s in the middle of places like Cambridge or Berkeley, we saw that society, as we knew it, had no way to cope with the ferment, the student unrest, the challenging of the old judicial systems and paradigms and things. Society had nothing to offer, and so what happened was that they squelched it. But that didn't make the energy crisis go away, and it didn't make the necessity to import oil go away. And the technological solutions, the revolutionary technological solutions, which are necessary, have to be accepted by society.
It was your, I think you mentioned previously that you were teaching classes. You were teaching a number of classes in electrical engineering at MIT.
Yes.
And the students were asking you questions you couldn't.
Yeah, they asked me questions I couldn't answer about the nature of temperature. One of them was, what happens after you go above the boiling point of water or below the freezing point? Is that the same temperature that we're used to? What does absolute zero really mean? And you discover that absolute zero is meant in terms of a definition of molecular motion, which may not have anything to do with what's really going on.
And you were working with Edgerton?
Yes.
Apparently, and Land was involved.
Edwin Land was my boss at Polaroid Corporation. I was head of a division of the research department, which was in charge of advanced three-dimensional motion picture processes. And Polaroid and MIT were right next to each other physically. You could just walk 2 or 3 minutes one to the other. And Land himself, Dr. Land, was a professor at MIT. So Edgerton, of course, was the hub of all the photographic interest at MIT as well, high-speed photography. So by working at Polaroid and working for Edgerton, I was in the midst of the two people that did, really advanced photographic science in their era.
And you had mentioned Harvard.
That's right. I went to Harvard Graduate School in '62.
For
applied physics.
Applied physics.
But I found it was too theoretical, and I wanted to go to get more experience, not learn more theories.
So you went to MIT?
No, I went to MIT, and then I decided I'd go to work for Polaroid. So I went to Harvard first, then I got the job at Polaroid and continued my work at MIT, which led into the teaching. And eventually I got an appointment in '67, which went all the way through till '71 as a lecturer.
Lecturer?
In electrical engineering, yeah.
What degree did you get from MIT? Then?
Bachelor of Science.
In AA?
In electrical engineering.
Right.
And physics.
Yeah, and physics.
And physics, yeah.
When did you start to get into the space power generation in terms of how Tawari might describe it, or in terms of looking at the equations of electrical engineering in new ways?
That's an interesting question. I would say I got into that because in the early days I had various phenomena which showed me that there was excess energy. I had the dropping of a rotating object which dropped at a greater rate of acceleration when rotating than when not rotating, even if it was in a box protected from the air.
And these were two experiments that you used gyroscopes and you also used spinning ball bearings.
Yes, and I found the elastic collision of a rotating object in a box suspended on bearings with another non-rotating object conveyed more energy in that collision than was supposed to. Energy was created in elastic collisions with rotating objects.
And then there was the Accutron watch experiment.
Well, the Accutron watch experiment came later, yes, because I thought that with all these inertial effects I had discovered, which are easy to see if you know they're there. I told you that you could pick up a Dremel or a Moto tool and turn it on and shake it along the axis of rotation, and you'll feel it feels more massive than if you move it perpendicular to its axis of rotation. And the inertial mass increases for experiments along the axis and decreases for motions in the plane of rotation. And if you know it's there, you'll say, oh yeah, there, I can feel it. But science doesn't allow that that's the case. And then I thought, well, if that's the case, then this effect must be impressed on the space around the object too, just like magnetism or charge or radioactivity or heat. So I decided, well, something that would affect inertia, inertial mass, should affect the tuning fork. See? And it just so happens, turn that off a second, Dinner. Well, this is a tuning fork, for those who haven't seen them. It's used to tune pianos, and it just is elastic portion here and two tines which vibrate back and forth, and the frequency is determined by the elasticity of this part and the mass of this part. And so a vibrating object like this brought into the field of a rotating object should vibrate at a different frequency depending on whether it was vibrating in the plane of rotation or perpendicular to the plane of rotation. And this led to the tuning fork experiment, which in fact detected that.
And this was basically to look and see if there was an inertial field associated with space that would affect the inertia of another object.
Yeah. Now you know, there's been
this is totally beyond what the realm of physics is as we knew it at that time.
But yes, you see, I had a terrible, at the time, I tried to talk to Dr. Wheeler at Princeton, the inventor of the black hole, and also with Weber, who was the guy that came up with the gravitational wave hypothesis, and tried to get them to understand that it wasn't gravitational waves, that it was waves of inertial mass, that inertial mass of objects was slowly fluctuating. And they just absolutely would not hear this, you see. And it goes back, getting back to tuning forks, why did I I've always been interested in tuning forks, believe it or not. And one of the most interesting things that before I knew anything about anything, was that why weren't tuning forks steadier than they were? You can take a tuning fork and make it out of Invar, which has its temperature properties, coefficient of expansion fairly zero over a range. You can put it into a triple thermostatically controlled proportional oven, and you can control the temperature to a millionth of a degree, and yet you'll still see it vary parts of 10 to the fifth, and you say to yourself, well, what is happening with this thing? And I could never understand where these variations were coming from. Now you can say, well, the Q, the oscillation is high and it's just noise and stuff like that, but these arguments didn't play on me.
That the inertial mass of the universe flexing through
Yes,
the area.
yes. And so, right, that's exactly what's happening. And of course, all these measurements that Weber was making about whether gravity was fluctuating was not what he should have had. A vibrating object, not a big tank of cleaning fluid. See, there's big science again. The bigger the experiment, the more money you get, the longer you've got your salary. And who cares whether it makes any difference or not, or whether it's fundamental? So anyway, they just wouldn't hear this.
What is the state of physics today, and have they begun to look at all at this type of experiment or this inertial mass?
Yes, physicists are beginning to look at this now because students, for the most part, have given up studying physics, and they've lost a tremendous following to the other sciences like the life sciences, biology, medicine, chemistry. Because they don't have anything to offer. I mean, if science is so damn powerful, then why can't they take care of the ozone hole or the smog problem, or give us an engine that doesn't fill the world up with smoke if they're so damn impressive? And students who have ideas about science and go to school and have a bunch of weighty professors come out and say, it's impossible. We have the conservation of energy, which shows that when you burn it all up, it's all gone and you've got nothing left but ashes. I mean, there's not a promising future in that, you see. And that's why people aren't studying it anymore. So,
What your first end machine experiment? What precipitated that?
well, I was working on gyroscopes for a long time, and I found all these interesting.
You found a gold mine in the basement at M.I.T.
Yeah, old machines, but they got rid of those as fast as they could because the theoreticians don't want exceptions. They don't want to build up some huge theory and have somebody say, well, but what about that? See, that's not what they want.
Did you begin instrumenting the gyroscopes as end machines then, or not?
No. I had done all these experiments on gyroscopes and found these very interesting properties, but nobody understood what I was talking about, because very few people are in contact with mechanics. And mechanics is considered completely known, it's been around a long time.
Yep.
So I had to switch into a field where instruments were accurate enough. What are you going to measure force with? An accelerometer? Who's got a few of those around? Scales, accurate 2 milligrams. Do you have a few of those in your backyard? But you have milliammeters and voltmeters, and you can counters. And if you translate the whole thing into the electrical realm, then you can make very accurate measurements which other people believe. So then I thought, well, if this gyroscope is so peculiar in its behavior, there ought to be electrical phenomena which reflect that too. And so right in my head, just as I'm meditating on the subject in the afternoon on my walk, I thought, what happens if you magnetize this thing? And I imagined the magnetic field sitting still in space, just like Faraday, and the wheel rotating through its own field. And I said, well, there ought to be a voltage between the axle and the outer edge. But then I said, well, what is this going to drag against? And it suddenly hit me just so clearly that there wouldn't be any drag, there couldn't be any drag. But I still didn't know how to explain it. See, that was enough to make me go build it. And then I had to start figuring out what was it, you see, which took me all the way into the 20 years or 25 years later. This figuring took me into re-understanding magnetism as a distortion of a primordial field. Now the thing is, physics is beginning to recognize this now, because it's reached the end of its rope in all the old concepts, and so they too are beginning to accept that this is here, that there is an overall field which determines things like inertial mass, and from which energy can be extracted if it can be distorted or polarized in certain ways.
When did you build the first end machine where you measured an over unity?
In 1978 in Santa Barbara, as part of the Sunburst community, because every businessman and scientist in town came to me and said, "By God, this is the greatest thing that ever happened. We got to go for this." And then nobody ever came back a second time, over and over and over and over and over again. And later on, people kept on telling me, well, they started thinking what it would do to the stock market, or the fact that they couldn't control it, and they didn't want to touch it. Or what would the government do?
Backing up to another homopolar experimenter, did you ever, in the M.I.T. time, when you were, or at Harvard when they were lecturing, did they discuss Tesla at all during?
The name Tesla was never mentioned. Edison was mentioned once in a while, only to say that we don't like him too much around here. He was just an experimenter. Tesla was never mentioned at all. And as I told you, I had two professors, one Dr. Trump and...
Trump, that's right. He played an important part in the Tesla mistake.
That's right. I had Dr. Trump and I had Dr. Gray, Truman Gray, both of whom went down to see Tesla's memoirs when he died. And they never mentioned Tesla. I just find it incredible.
Yeah. Trump was commissioned to go through the multiple cases of Tesla's material and produced a report that said there was nothing there.
Mm-hmm.
However, interestingly enough, later on, the Army commissioned a man to spend time with Tesla every day for 6 months and go through Tesla's pages piece by piece. This was just before Tesla died, 6 months before he died. The Army went through everything Tesla had and extracted information they thought was valuable.
Well, it's probably in some file somewhere.
Yeah. So the end machine test at Sunburst was what range of efficiency were you looking at? What kind of parameters, RPM and?
The first test that we made at Sunburst was we made a big solenoid, about 13 inches in diameter, and wound it with copper wire and put slip rings on the shaft so we could energize it. And we mounted it on the bed of an old lathe, a real old lathe, 1900, a converted wood lathe with a Ford Model A transmission to change the speeds on it, believe it or not. And in the beginning, we had a 0 to 2,000 RPM permanent magnet DC motor of about 1 horsepower driving it, so we could go up to 2,000 max with a lathe steady rest on there, plus the headstock that was holding it. And we got at 3/4 of a volt, we were getting currents of around 800 amperes and efficiencies of 2.5 to 3 to 1 DC output versus DC input overall to the drive motor at the time. And all kinds of people from all over, including the CIA, finally eventually showed up to see those demonstrations. And then later on, when the machine was completed, to complete it meant that it had to be mounted in a completely non-magnetic surrounding, which in that machine was brass and wood. You can see this machine is completely non-magnetic. This is a phenolic case, a transparent top, 1 inch thick. Every bolt in here is non-magnetic stainless. Everything, all the fittings are aluminum and copper, so there's no magnetic. The closest magnetic material that's fixed in this thing is the drive motor on the axis back there. The base is wood. So any kind of magnetic material brought near one of these things will throw drag into the system.
Yeah. What N machine? How did that terminology or that term come about?
Well,
What does it stand for?
Well, N means the nth degree. Because when it first came into my head that what I should call this thing, I guess I can say this now. When something happens like this, like somebody coming up with a simple way of extracting energy from space, which will transform society, or at least spark the transformation of society from a consumptive to an outgoing, expanding situation. It's a very special time. It's like everything contracts down to a point and then expands out from a point. Chardin, in his work about the future history of man, talks about this point. I believe there's a myth to free energy in that in any intelligent society, in any planet in the universe, when it reaches the point in its intellectual development where it can conceive that this is a possible principle, the same people, the same souls are manifest to do the same job. So you have to say to yourself, why did I call it the N machine? Because it was so clear in my mind to call it the N machine that I didn't have to think about it. It just came, just like I knew it wouldn't have any drag. I also knew I ought to call it the N machine because I knew that there were N things that would come out of this thing, that this would change our way of thinking, our way of living. This would take us into space, which is where I really think the human race is destined to go, and provide the power plant for the spaceship with a non-consumpting or consumptive source of energy. So that's a very, for the people that work in this field, I think you've met others who felt the same way. You feel like you're at the focal point of a great societal happening. It isn't as if you're like in an ordinary situation anymore, especially if what you're doing is real and it works. Now, this thing is not simply just a machine that I tripped over in my garage and produces more energy than it consumes. This machine represents a whole new take on the physical reality we call the world. It represents the start of a whole new physics which includes gravity, inertia, ether, free energy, primordial fields, you name it, time. Space. Right. So the thing is, this is a pretty interesting little box in terms of what everything that comes out of it.
Right. It implies a whole new science and technology.
Yeah, and a whole new direction for the world to take out of the doldrums that it's circling around in now. So when things happen with these things, for those of us who've suffered the frustrations of trying to get this into the world, what you eventually come into is you succumb to the natural flows. You realize what you're doing is inevitable, so you don't fight it anymore. You just go where it takes you, and you just keep putting it out, just like I'm doing right now. And it all adds up to something.
Yeah, it sure does. Can you maybe describe a little bit how you conceive that energy from the ether, from space, is coupled into and ends up in the shunt? It ends up in the external drive circuit?
Yeah, I can talk about that. But to talk about that takes you into the realm of new science. Now, you can make statements like this, that this pre-existent field, this ether, this whatever it is out here, has the capability of being polarized. It has two aspects to it. It goes back to ancient philosophical takes on the universe, that there's the light side and the dark side. Everything we do, we sleep and we are awake, it's night and it's day, it's black and it's white, it's on and it's off, and it's up and it's down, and it's in and it's out. And we're confronted with these polarities, all through positive and negative. And the most basic polarity of them all is male and female, from which all the other polarities are derived. So what you can say is that this space we exist in has the capacity to elicit the two polarities, the male and the female, if distorted in the appropriate manner. Now, those two polarities of the male and female can emerge from a machine like this as positive and negative electricity. And you see, our present conception of electricity is that we have these two cables, and say one is positive and the other is negative, and we have a load down there. In this case, this would be in a bucket of water to absorb all the energy. We would say the electrons go down one cable, go through the load, and then come back and go back into the machine. And this whole idea of the flow of electrons and the continuity thereof is another expression of our idea of the conservation of energy, where there's a fixed quantity of something and it circulates around, it's pumped around. But if I were to interpret this machine in the way that I see it, I see that what's going on in here is through the setting up of a centrifugal force field, just simply due to its rotation, we can distort the space around the magnet, and we can elicit the male and the female polarities. So what we have here is not positive, but we have male, and what we have here is negative, and we call it female. And what's happening is the two energies are merging in the load and producing heat. You see, and the heat is being absorbed back into the environment where it originally came from in the first place. So if you measure the same current flowing in here as you measure in there, this doesn't mean that the electrons are going that way in this one and that they're coming that and that way. This just means that you have an experiment, which is in a little electric motor with a pointer attached to it and springs, which you stick in series here, and you say, well, that indicates the flow of the current, but that's only your interpretation of this thing. Maybe this meter is actually sensitive to the male component of the polarization energy.
Yeah, you mentioned Shakti.
Yes, Shiva Shakti, right.
Principle. Could you go into that a little bit?
Well, that's the Shiva
The reason
Shakti.
I'm interested in that is because it was Tesla was using Sanskrit terminology to describe this
Well,
in the 1800s.
right. Well, the whole Hindu philosophy says that the energy of the universe comes from the merging of the male and female principles, the Shiva and the Shakti, and it's the merging of these two rivers at the head of the Ganges that generates the whole created world. So it's just another way of denoting the two fundamental principles, the male and the female. They don't call it male and female, they call it Shiva and Shakti, but it's the same thing. See? So there's a more... My next paper on the subject of electricity will be to show that our interpretation of electricity is not simply determined by the measurements we make in what we call electrical experiments, but it also has to do with what we think about conservation. You see, and if we would give up on the idea of conservation and get down to the thought of the basic polarities of space and the merging of the same to produce energy, I think is a truer view of what's going on than the idea of electrons being pumped through this thing. Now maybe the electrons which we observe in experiments like the milk and oil drop experiment and electrolytic experiments, which Faraday did, maybe these quantized charge effects take place right at the electrodes, and what's flowing through the cables may not have anything to do with what we see coming out the ends of the cables. I don't know.
Right.
See?
Batteries running low.
We were talking about the future, and I really feel that in science there won't be too many people who want to sit in a laboratory all day and all night working on science when they could utilize the freedom that this machine will give them. To it, you see, with this kind of machine, if you get this thing, you don't have to go back to the gas station or the dealership. You can take one of these energy machines and you can live in the middle of the desert underneath the water. You can make a spaceship travel through the air. You're independent. You can enjoy life. You might want to grow flowers. I don't know. Why do people study science and engineering now? Promise of great careers. What do the careers generally have to do with big military establishments? If there weren't any big military establishments and people were more into just plain living, then there'd be a lot less interest in high-paying jobs supporting the manufacture of, big and military machines. I really think the study of science will probably go back to the way it was in the days of Newton. There'll be a few universities where scholars and people interested in these kinds of things will congregate. But I think this society is interested in space travel. I think it's interested in exploring the universe, but I think it's also interested in entertainment and virtual realities and things like that. And if you provide a new source of energy and you eliminate the pressing environmental problems which are upon us now, and society's great challenges of food and space can be conquered because we can turn the rest of this planet, which is arid or presently unlivable, into living space, then what will people do? They'll start living. And for some, living is designing energy machines, but for the most, I think living is having fun doing other things. So without this great military machine going, I don't think there's going to be a lot of interest in science. And you're showing me these books where we have architecture and rugs and paintings with symbolic pictures, which might be the rotors of future energy machines. But if you think about it, who's going to care about whether or not there's a primordial field, or where the energy comes from, or whether it satisfies the laws of who knows of what? All they'll be wanting to do is put one in and turn it on, and people in general are not going to be interested in any more in this than they would be in their telephone or refrigerator, how that works. So they're going to be interested in doing things and going places primarily. So
I see what it does is it frees mankind up to pursue the spiritual nature of itself. It puts people back in touch with the family, with the kids.
With it, yes.
It gives them time to contemplate nature, reality, and
that's right.
And what they're about.
Yes, and I think we can start becoming the civilized society that we're supposed to become, and stop preoccupying ourselves with fighting over bits and pieces of something which is getting smaller and smaller, So yeah, I think it's going to make a big difference. But it's not important to me how many scientists there are, or how many students there are. It only takes a few people to get this thing going. And after that happens, everybody can choose the environment that excites them the most. I'm interested in spaceships and going to other planets, but other people might be more or less interested in a free energy heated hot tub or a swimming pool instead. So, they'd be even happier than I would. So, All right, now getting back to this particular machine. After all the years of working on these machines and building many different experimental models, and of course being in touch with everyone else who talks to me about this stuff around the world, there's certain requirements which emerge that in order to make a valuable commercial product which people can afford, you put it all together into something. And this machine seems to me to incorporate most of the things that I think will make this commercial. Firstly, it has a very high power output because its internal losses are very low. In terms of the construction, to understand it more clearly, here's just a little sketch on the bottom of a piece of note paper. This machine incorporates a rotor, the cylindrical
And that's the magnet
section.
Oh, okay, that's
And then the rotor is a conducting tube into which are inserted two magnetic slugs, in which the light poles, in this case the north and the north, are facing each other, so that the flux from the poles comes out and curves around and comes out perpendicular to the surface of the conducting tube, which is between the two magnets. Now this bending of the flux lines can be facilitated by shaped magnetic slugs and things in here too. But the general idea is that the repulsion of the two magnets forces the flux perpendicular to the surface of the tube. Now, if the flux density was uniform and we rotate the tube, the voltage that's developed between these 2 points is equal to B, the flux density, L, the distance between the points, and V, which is omega r, which is the tangential velocity of the tube. Now this configuration is useful for this reason, that in a disk, when you rotate it and you go take your voltage from the center to the edge of a disk, the velocity of the center of the disk is 0 and it reaches a maximum when you get out to the edge. And so the sum of the voltage is equal to the integral of voltage starting from here all the way out to the outward radius. And it's a variable. Whereas if you measure the voltage along the cylindrical section, it's constant because the flux is constant, the speed is constant, and the only parameter is the distance. So if you take the same amount of flux as coming out of these two magnets and force it so that it comes out through an area equal to the surface area of the two magnetic poles, then of course you can get a uniform flux density coming through the surface of this disk, which is equal to the surface flux density on the surface of the magnets. It's uniform, and because of the increase in velocity of this part that's getting the voltage, you get 4 times the voltage between these 2 points as you would get from the center to the edge here. And so that in terms of a given size magnet slug, and these are neodymium magnets, you can't make these too big because the manufacturing possibilities are not so good for slugs over 3 inches in diameter, and these are 3-inch diameter slugs. So with a small slug like that in normal conditions, you don't get much voltage at manageable RPMs. But with this setup, using 2 slugs facing each other, we wind up with 1/10 of a volt per 1,000 RPM, which means that at 10,000 RPM we get 1 volt from this thing. Now because it's mounted in a strong supporting cylinder, there's very little speed limitations of this. You can only limit it because it'll eventually blow up or burst. So our rotor, which is 3 inches inside and 5 inches outside, can do about 30,000 RPM before it'll blow up, which gives 3 volts output. And since our voltage is taken across the length of the cylinder, and you see on this machine here are the 2 current collectors, the cylinder rotates between them inside this box. There are mercury contacts on the 2 current collectors, and you can take as much current out of this thing as is limited by the heating of the rotor, and the rotor contains the magnets, and the magnets can only take about 100 degrees C. But because the internal resistance is just as low as it can be, you only have a straight section of tubing between here and here, and no convolutions or anything. So our internal resistance on this machine, including the mercury, and including the current collectors out to this point, is 10 microohms, which is as low as I've been able to do in any of the machines I've made so far. So this machine has 2 support bearings on either side, and these are oil drippers which drip the oil in very slowly. 2 current collectors which enclose the rotating central shaft, and mercury is sent into each collector from these barrettes. And the way this system works is in all the systems I use, it's a centrifugal system which has to be running when you introduce the mercury, so the mercury gets carried around by the rotating member and forms a bead between it and the fixed collector. And of course when you stop the rotor, the mercury runs out the bottom and comes out these tubes, and we recirculate it and recycle it back here. It does, for machines which rotate at these speeds, you can't use any kind of contacting seals. So anything you make is going to leak a little bit. This just leaks a little bit. So the mercury flow through the collectors is only a couple of cc's per minute. So a thing like this, as it slowly went down and dripped in, would run at about an hour under normal. So it's very slow flow. So on the other end, we have a drive motor, which is the latest in technology, with a samarium cobalt rotor, permanent magnet, 3-phase AC excited, variable frequency, with 97% efficient 5 horsepower drive motor on this thing. And this is a torque arm which is sticking out the side, which we put a scale on to measure the exact torque input, and then times the RPM gives us the exact horsepower input to get a certain amount of electrical power, which is absorbed by that shunt, which is in a bucket of water to water cool it.
What kind of torque are you getting, or horsepower input, then, using this?
In the experiments we've performed, we're about what was it, about I think on the order of 0.8 foot-pound or something, pretty low. It's not a lot. Mm-hmm. And a maximum input of about a horsepower in our early experiments. And this is the first time, it just so happens you've shown up at the point where we've just completed this machine and it's in its testing phases, and we've just installed this motor. We're going to hook it up perhaps in the course of this chat. But this is intended to be a kit for the construction of a machine with very carefully measured parameters, which produces overall more output than input on the order of 2 to 1. So for every electrical horsepower that goes in this thing, 2 electrical horsepower will come out. Now, this could be the basis of a self-running electric engine, and the purpose of providing this kit is so that one could assemble this thing and test it, and then all it takes is an inverter to go from the 0.5 volt or 1 volt or 2 volts, whatever you want to run the speed at, to invert it to the 300 volts the controller needs to run this drive motor. The overall efficiency of the controller is 95%, the motor efficiency is 97%, the overall efficiency of the combination is 92%. The overall efficiency of this is 2 to 1, and if the inverter can probably come in at 90%, then you'll have enough to make it self-sustain.
What's the current rating in the, let's see, this was how many millivolts out the cross?
That's 100 millivolts for every 600 amperes.
And you're expecting what kind of current out of here?
Well, the currents we've gotten now have been, this pulls 950 amperes at 0.27 volts, so if we double that, it's about 2,000 amps at a 0.5 volt. We run it up to 3/4 volt, it'll be 3,000 amps. You see, we have to be careful here, because with these high currents there's heating, and the heating heating is right at the joint between the collectors and where these copper cables go in. This probably could be improved. And that eventually gets into the rotor, and we don't want to let the rotor get too warm. The fact is that we have a very wide mercury contacts. They're 1 inch wide, 15 square inches on each one. This is a very good way of conducting the heat out of the rotor into these, but also a good way to conduct heat into the rotor if the cable connections are getting hot. So the purpose of this breadboard is to give people, and experimenters, universities, or whoever wants to get into this field, something to begin with, so that they can start performing experiments with bearings, speeds, drive motors, inverters, because all of these will have to be tailored to this particular situation. Also, I might point out that We're just using 3-inch magnets in here. Anything larger, if you're going to use neodymium, you have to fabricate by gluing the smaller magnets together, which we've done. I've made 12-inch diameter rotors by gluing in 2-inch wide hexagons, which is a very tedious, expensive task, but nevertheless possible. But if you make this, say, a foot in diameter, then you're talking 24 volts at 5,000 or 6,000 RPM. And if you make it 3 feet in diameter, a meter, then you're talking, something 2 or 3 megawatts output, and your output voltages are up around 150 or 200 volts, easy to invert. So the only real inversion difficulties are going to happen at these small sizes and low speeds. But build this thing up in size, and your inversion problems are going to go away. See, and your power is enormous. You only have, it's the simplest of all possible generators. It has no stator, 2 bearings, 1 rotor, and the current collectors. It's essentially a rotating member and 2 fixed members to feed current in and take current out.
So this particular machine, the overall kW output rating is about?
You can take as much power out of this machine as will heat it up. And you can make your own you can take as much as 50 or 100 kilowatts out of here for short times with this internal resistance of 10 microohms. But like I say, the heating will eventually cook this rotor over 100 degrees C. So we're figuring steady, maybe 10,000 amps. We can run it for 10-15 minutes at that current before the heating gets too bad. But what that's saying is that here again we're getting back to this breadboard. Would you rather we sell you an expensive contraption with a refrigerator, an air circulator, maybe water going through the rotor, or would you rather figure it out yourself? Anybody who sees this get warm can figure out a scheme for cooling it. It's not, I'm not trying to be the last word. I just want to give people the minimum. And when we talk about minimum, I think we could probably sell this thing for $25,000 American. See, they can buy this and get themselves set up to start doing experiments with free energy. And from then, of course, with the money that we make with this thing, we'll keep expanding it and developing the technology and feeding it back into this. But the important thing is to get a machine which people can buy and understand and start applying right away. See, and that's my strategy. Now, you can tell me all about secret deals and offshore factories and Japanese, you name it, but I still think publicity, simplicity, and human ingenuity are the keys to this. It's as if we had the internal combustion engine, which in the old days you could make in your own garage. Same thing with early electric motors. And human ingenuity, American inventiveness went to work on that. And now we have the kinds of automobiles, the smooth, completely different form of energy, internal combustion. You get in that car, it runs like an electric motor. See, that's a lot of perfection, and no single inventor can do all that. So I'm just saying that here's the principle, and from then on, it's going to have to be everybody that's involved in this, and I just want to get it out. See, that's the purpose of this whole exercise here.
Great. I guess that pretty much says it all. Well, we'll take that off there. I want to get a close-up view of just the internals with the camera.
Yeah, go take a look down from the top.
Okay. Let's do that.
This machine does about 2.7 to 1 incremental.
Okay, what we're demonstrating right now is the magnetic field on the surface. At the surface, you can see the wrench swings in.
That's perpendicular to the surface, right in the center between the current collectors. And then at the ends, it's parallel to the. You can see here. Parallel to the axis. Sort of like that.
Parallel to the axis of the machine.
See that?
Okay.
Will curve in.
Curves in, flex curves in, okay.
This construction has never before appeared in the literature. There have been cylindrical machines made, but they always used external pole pieces, which would complete the magnetic circuit between this and the outer end of the axle here. No one ever thought that the machine would operate if you put the magnets inside the cylinder and rotated them with the cylinder.
Okay, and these are the brush. There we go. Here's a balanced.
Yeah.
Real balanced now.
Yeah.
We're taking the brushes off, then
This
are
is
here
where
and
the
here,
current
and
collectors, right?
the
Yes.
current collectors are here, and
Yeah.
the rotor is on the
Yeah, the
inside.
rotors in the center, and those plastic things are part of the seals.
And I don't know if we mentioned before, but these are
Oilers.
oilers, lubrication,
One drip every minute or so.
drip a minute.
For very high-speed bearings.
Yeah.
Okay, I'd say that's pretty good.
And the cables can be used on either side of the machine. You can take them up on both sides simultaneously.
Okay, I'll get that. We've got brass lugs coming out both sides of the machine.
My finger can go in.
Yeah, there's where the outputs are on both sides. So you can take current off both sides. Two outputs.
Now this box is an inch thick to make sure that nothing happens. Anybody that tries any of this high-speed rotating stuff, make sure it's blow-up proof, because you can get killed. This is like a bomb when it goes off if you run it too fast. And people always want more power, and the easiest way to raise the power is to run it faster, so beware.
Yeah.
Power and output goes as the square of the speed. Losses go directly as the speed.
You're now on camera, Paul Clark.
Thank you very much. I'd like to first of all thank my sponsors. That's God in heaven, Holy Spirit, Ether, Dynamic, Energy C, and my mother.